Merci. Yeah. Now we will welcome Alice Hooker-Stroud. She's from the Center for Alternative Technology in Britain, and she was the leader of the Zero Carbon Britain project, so she's going to present that to us.
Thank you, and thank you for having me here. Thus far, I've really enjoyed all the discussions that we've had, and I hope we'll have more over the next few days. I'm aware that I have an advantage over a lot of you with English being my first language, so if I do speak too quickly, do something like this, and I'll try and take notice and slow down. Slow down. Okay, so yeah, my name is Alice. I work at the Centre for Alternative Technology, which is based in Mid Wales in the UK, and I work on a project called Zero Carbon Britain. And I'm going to talk to you a bit about balancing variability in a 100% renewable scenario, which is a question that's come up a lot. I expect a lot of questions at the end. But first off, I'm going to tell you a little bit about my background. As I've been chatting to people over the last few days, it's been quite a common question. Where I come from, who I work for, which is actually quite different to a lot of your situations. I don't work in an academic institution. I work for a charity. And this is what the Centre for Alternative Technology looked like in 1973. It's a slate quarry in the middle of Mid Wales that had been abandoned, disused. And it was set up by a group of idealists. In essence, people in the 70s who decided after the oil shock that we needed to really rethink our energy systems, both supply and demand, and do things very, very differently from how we'd been doing them previously. This involved, for example, this is the first building that was put up on site. It's still one of the most energy efficient buildings in the UK. And it's now almost 40 years old. Unfortunately, it's not a very nice place to live, apparently. You can see the windows are very small. The walls are also about this thick. Thankfully, we have better technology now. We don't have to do this. They also looked into trialling and testing what were then very alternative technologies that now we're talking about in very commonplace. Most of the scenarios that we've discussed at least have some place for renewables. So these are solar thermal systems that were being trialled and tested at the time. This, quite hilariously, is the first wind turbine that was put up on site. This was the main generation of electricity for this group of people who lived off-grid for a good number of years at this site. They also recognised very early on that energy storage was incredibly important. And this is their first effort at building an energy store. So it's an underground energy store of water. Now the centre is quite a different place. No longer looks like a trash heap. We have some really nice buildings. But we also have quite a different function. So we're no longer such a trial and testing bed for these innovative technologies because most of them have been very well developed and we actually know very well how they work and we know that we can rely on them. We run educational activities. We run short courses in sustainable building methods, open source technology development. We also now have a graduate school for the environment where we run master's courses. So we take all of the things that we've learned over the last 30, 40 years and we tell everybody else about them. This is our most new building. This is the Wales Institute for Sustainable Education, which has won an award in the UK for being one of the most sustainable buildings in the country. This is the lecture theatre. You can see just an example here. In the walls, they're actually built out of rammed earth. So they're literally just soil that you take from the ground and you compress it. And it's a very, very low impact building material, but it also, again, acts as an energy store. So it takes the heat coming through the windows, stores them, releases it over a longer period of time. The courses that we run are very practical. So we really get people involved in the renewable technologies. We get them to trial and test everything themselves. And actually the project that I work on is vastly different from most of the activities that happen at the Centre for Alternative Technology. It's much less hands-on and much more sitting behind a desk and doing sums, which is a bit unfortunate for me. But what we end up doing is that we're trying basically to make what we call a technically robust scenario in which the UK has risen to the challenge of climate change. And I'm just going to clarify something here. I want to be entirely sure that you understand when I say scenario, it was talked about earlier as a vision. So it is in fact a time slice in the future. The only development that we've done from here to there is to actually just draw a straight line and see what kind of development needs to be done in the middle. So it really is just looking at exactly where we need to get to. And as Eve said yesterday, yes, it is a Dear Santa. This is what I would like to happen in the world. This is my vision for a positive future. But I'm going to touch on this at the end, which is why I actually think, despite not having that roadmap, it's still a very, very important exercise to do. So first, some assumptions. We take this as a physically realistic approach. And what I mean by that is that we say business as usual is not an option. And I don't mean that from necessarily just from we can't keep doing the things that we need to do because climate change will happen and that's a bad thing. I also mean from a perspective of if we do go along the business as usual route, the change to the situation in which we live will be so different that we can't possibly continue with the activities that we're doing at the moment. So this isn't a future that is obtainable for us. And when we look at something that is more politically realistic rather than physically realistic, we get not further away from that business as usual, actually. Even with all of the current emission pledges that we have, it doesn't take us far away from this quite regular and quite upsetting future, actually. And most of the models that we've been talking about, I would sort of put in this side of this chasm. This is how we sort of frame zero carbon Britain. So over here we've got political realism. We've got questions like, oh, if we looked at how much economic growth we need to keep people warm and safe and happy, what changes could we make within those constraints? What kinds of changes could our politicians make that we would accept? And they're mostly on this side, and they don't really take us across to this side of this chasm, which is actually what, when you talk to climate scientists and you read their work, what is required of us to be able to avert this 2-degree temperature rise. So we're really not quite getting there with these sorts of models, which is why what we're looking at is kind of what is required to be on that side. And the impression is that we need to know exactly where we need to get to before we can start going there. So it's a physically a realistic approach because we can't change the physics, right? And essentially for us in the industrialised West, who have been emitting greenhouse gases for a very long time now, and we've been reaping the benefits of that, it's basically net zero emissions as soon as possible. If we can do it next year, if we can do it the year after, great. I know that pretty much all of us in this room thinks that that is completely impossible, but say in the next 20, 30 years, this is what we need to be aiming at. And that's greenhouse gases, including methane, including nitrous oxide, not just carbon dioxide, and from all sectors. So not just energy. We need to be talking about agriculture, our land use, our industry, our waste processes. And someone mentioned this yesterday, and I think it's really important to remember, even if you're not aiming at zero emissions, getting those emissions down from sectors that aren't energy related are so much harder. It's so much a harder process than those related to energy that you should probably aim at zero for your energy systems anyway. There were a lot of people who sniggered about the mention of change of diet earlier, but actually, if you want to get your agricultural emissions down to zero, you're going to have to not eat meat and probably not eat any dairy. So if you don't want to do that, even if you're not aiming at net zero emissions, you need to get your energy emissions down for sure. So basically our assumption is that big changes will be necessary. That's a given. And it's certainly a big change to get from here at the top. I'm of course talking about the UK, but I doubt France is very different. We have a lot of greenhouse gas emissions currently. This is 2010, our baseline. And in essence, this is where we end up in our zero carbon Britain scenario. So we've pretty much got those energy emissions down to zero. We have some additional effects from the aviation remaining in the scenario. And we still have some remaining emissions from our non-energy processes and from our land use. But we managed to net those out with a clever use of our land use to capture carbon, which I will not go into, but you can come and talk to me about later if you want to. And alongside this, we try and Basically, we're trying to create a positive future for people to look at. So we're trying to be quite aspirational in our vision of where we're going. So we have some aims that we're trying to get to in our scenario. We want to keep the lights on, make sure everyone stays warm. It's very important. That's our supply meets demand kind of thing. We also do look at diet. We look at nutritional aspects of diet. We look at the greenhouse gas emissions associated with our diet and how much land that uses. That's a separate part of our model. But we need to make sure that we're all eating enough, we're eating well. We need to keep a decent standard of living and the benefits of the modern society that we have today. The last thing is an additional part that we look into when we use our land use part of the model, which is we need to support biodiversity. Climate change is just one of many issues that we're having currently. And we need to actually look beyond carbon at the impacts that we're having. So while we're designing this scenario, we try our best to use less land than we do currently. And that's both at home and abroad. So, sorry about that long, detailed backdrop. I just wanted to tell you exactly where I was coming from. And I'm going to talk you through the energy aspect of our zero carbon Britain scenario. We've got some rules, very similar to the presentation that was just given, I suspect. 100% renewable energy, that means no nuclear, no CCS. We don't believe that they are actually sustainable solutions. We're probably going to eventually have to get to 100% renewables anyway. If we're going to make major changes in what we're doing, why not do that now? In our scenario, we also only use UK resources. This is important for a couple of aspects. One is because it's actually much easier just to model the UK for us, rather than having to model the rest of the world as well. And the other thing is that if we can prove that we can be self-reliant in energy, if there is a possibility of importing or exporting and that is advantageous, then we can do that. There's nothing wrong with that. But we need to know that we can do it alone if we really need to. And finally, we only use technology that we've got now. So I'm not saying something that is, for example, at price parity with the market. I'm not talking about something that is going to be a cheaper option that we have now. It's probably going to be expensive, and it's going to have to be massively scaled up. But it's been proven that physically it works. It does what it says on the tin. And we're not relying on any silver bullets because we need to do this now. So we're not relying on any technology that may be developed in 20 or 30 years' time. We've got everything we need at the moment. We just need to use it. So this is our energy system today in the UK. Largely fossil fuels, not so much nuclear, very little amount of renewables right at the top, and very large energy demands. And I'm also skipping to the end, and this is our energy system in zero carbon Britain. Vastly different. Much, much lower demand, much, much lower supply as a result. But largely speaking, I don't think any of those kinds of things are really new messages to us. I mean, we heard yesterday, it's basically a much reduced energy demand. This is through improved efficiency and also through some behaviour change. We electrify our systems and we decarbonise our energy supply. These are things that we heard about yesterday. We've just heard about again. It's not new. It's not a new idea at all. And in fact, the Centre for Alternative Technology published a very, very similar report back in 1977 that essentially said the same things. So I'm just going to focus on demand. I do actually go through the transition between the energy system that we have in the UK today and the energy system that we propose in ZCB. Our approach is broadly similar to what was just outlined. Actually, Yvonne, you go into a bit more detail than we do. But actually, I don't feel like I need to repeat exactly what has just been said. It really is very, very similar. And we do, unsurprisingly, come to very similar conclusions. We reduce our demand. We reckon we can get it down to about a 60% reduction in the UK. That's not 60% across all sectors. Industry stays roughly the same. The types of fuel that we use are very different, which is an important aspect. Basically, we say our population goes up, so our output would go up, but the energy intensity of our industry would go down, and they kind of roughly level each other out. In buildings, it's a very different story. In the UK, we have an incredibly poor housing stock. We don't have any insulation in our roofs, we don't have double glazing, we have drafty, not looked after, old buildings, and we can actually make huge energy savings simply by perhaps raising most of our buildings to the standard that you might be more accustomed to in places like this, you know, where you're actually making sure that you have good insulation, you make sure that you have double glazing in your windows. And the last step that we actually include here is kind of a little bit of a techno fix, but it's also it will change the way that you might use buildings. So we say that you only heat rooms that you're using, and we also say that perhaps the temperature at which you're comfortable on average goes down slightly. That's an average, and it's important to remember that it's an average. If you're older, you perhaps need a higher temperature in your room.
Just to know what surface, because we are more used to kilowatt-hour per square meter in year. What is your surface?
So the surface is the UK housing stock.
Which is?
I don't know offhand, I'm afraid. I can look it up. We do cater for some new builds, but this is actually looking at the housing stock that we have at the moment. Transport, again, we can make massive savings here in terms of our energy demand. This is in fact the biggest energy demand reduction that we can get, which is interesting because the UK government don't want to talk about changes to the transport system. So this one always gets some really interesting reactions from people in the UK. Part of that is saying that we do travel less. You know, perhaps we use things like teleconferencing, we Skype people, we might live a little bit closer to where we work, and we also change the modes that we use as transport. So there's still quite a lot of personal car use, but it has decreased from what we have today. Increased public transport, and we do a bit more cycling and walking for very short journeys. And there is an issue here that I brought up yesterday to do with aviation, which perhaps is specific to the UK. I noticed in your model, Yvonne, that you said that you keep the same amount of aviation. Is that right?
Yeah, we don't change it much because there was a study by the CCC which actually said even if you curtail business flights through video conferencing, it really is a small amount, it's all leisure flights. And you can't tell people not to go on holidays.
Well, we find, okay, it's partially because we try and produce all of our own biomass in the UK. So we want to cater for all our own energy demand within the UK, and we can't electrify aviation. And we include our international aviation, which we do a lot of in the UK, and we actually reduce how much we fly down to 1/3 of current levels. That's still enough for everyone to go on holiday once every 2 years. So we fly a lot in the UK. So this is our first portion of reduced demand. The second is basically free. It's electrifying our systems. We don't have to do anything. I still get in my car the same way that I might. Well, I don't because I don't drive, but other people get in their cars the way that they do normally. It's just an electric car. So this is our demand reduction. We've also changed the fuel mix. So this is the delivered energy, the type of energy that we get. You'll notice there's a lot more electricity there. And when we look at the supply, this means that we can actually ramp up our renewables. So we're just producing that energy, a large proportion of which comes from wind. And that's because in the UK, we live in a very windy place, which is very lucky for us. We should really make better use of this, especially in comparison to other areas of Europe. We really have one of the best wind resources in the world, and we're not using that to its potential at all. And this is how we model from the reduced demands that I've just talked about over here. So we've got our heating, appliances, industry, transport, and then we've got our supplies and the routes from one side to the other. I'm just going to concentrate on this for a second. Basically, what we do is we look at research that's been done about the UK, about the possible amount of energy that could be produced if we exhausted the supplies of these renewables. And then we say, well, do we need to use all of that? The answer is no. We don't really need to use most of it, actually. We could produce a lot more energy if we wanted to. So if we didn't want to reduce that demand quite as much, we could probably manage that. So we've definitely got enough resource on an annual basis. In fact, not my institution, a campaign organisation has done an assessment across the world which says if you take the energy demand in zero carbon Britain to be a good standard of living and you multiply the per capita energy requirements to the global population and you match it to the renewable resource that's actually available globally, then everyone can live the same. We have plenty. But the big question, that I'm sure you've all been waiting for the answer to. Is this a reliable energy system? This is something we get asked every single day. It's great. And now we have some answers, which is fantastic. So we term this as can we keep the lights on? Because that's what most people actually ask us when we talk to members of the public. It's not necessarily, is my granny going to be okay when she's in hospital? Are they going to turn the life support off? It's actually, are the lights going to go out? I don't know why they're so concerned about the lights. So I have two titles. It's either called Balancing Variability in ZCB, or if you don't like that, pretend you haven't heard that title, and it's how we deal with intermittency. And I have a couple of thank yous to say. Toby Kellner and Philip James are two colleagues of mine who did most of this work, and I really have to thank them. We also took a lot from Loughborough University. Our energy model is basically a development of the one that they made a few years ago. And finally, to the Fraunhofer Institute for Wind Energy and Energy System Technology, who gave us the idea of how to solve this variability problem. And finally, to members of the public. Our work in ZCB is largely communications. We do 1 year's worth of research to 2 years' worth of communications. And that affords us two things. One is it's important because when our government makes decisions that might move us in the direction of this kind of scenario, we need the public backing. They're too concerned that they won't get voted in next time round if they're going to make dramatic changes to what's going on. So we need to make sure that actually members of the public understand the problem and understand what the implications of the solutions are. The other thing is that they inform us on what else we need to look into. So actually, although you guys have all identified this as an issue, basically it came from the people that we spoke to for 2 years who all went, that's great, I really like the idea of renewables, but I'm not sure I trust that they're going to stay on when I need them. So we needed to answer this question for them. And this is our energy model. So we model the UK, not Britain. Probably doesn't make much difference to you, but in the UK, that's a very important distinction. We model an island system, which I've already stated, and I've actually realised that it's much more difficult, probably for most of you, to imagine that situation. But in the UK, we are actually an island, and we feel like that a lot of the time. So it's actually much easier for us to do that, and from that technical point of view that I mentioned earlier. We treat the UK as a single grid point. So we don't actually model the flow from a wind farm, for example, in Scotland down to London. That we have enough excess capacity probably to deal with losses that are inferred from that transmission, but we don't actually implicitly model it in the scenario. The temporal resolution is an hour, and we basically use 10 years worth of data. So this is historical data, so it's from 2002 to 2011. It's basically 88,000 hours worth of hourly offshore and onshore wind speeds, which are reanalysis work done by NASA. So they're validated against the one location that we actually have offshore wind speed measurements for, which is a weakness, but we don't have any more data. So we're using these reanalysis wind speeds. We've got data for solar radiation and wave heights from the Met Office. We've also got data from the UK government to do with our electricity consumption. And we've got a daily weighted average temperature, which we use to infer how much energy we would need to use on an hourly basis for our heating. So our heating inside our buildings is directly related to the temperature outside. We basically put this kind of, I guess it's a demand profile or a supply profile on an hourly basis onto the installed capacity of energy that we've got in our ZCB scenario. So how much electricity we're producing, and onto the reduced demand in our scenario. So we're kind of using a future energy scenario on an annual basis, but data from the past, which is a bit confusing, but it's the only way that we could figure out of doing it. And our energy model looks a bit like this, which loosely speaking is supply on the left, demand on the right, and then we've got this storage and backup system in the middle, which is crucial. I'm just going to give you an example of how we make those profiles. So we assign small areas offshore and onshore in the UK. We also do this with solar. The areas for solar are much bigger in the UK because we don't see that there's actually enough variation to warrant very small areas, and solar doesn't play a big role in our scenario anyway. Basically, we feed in the data that we've got from NASA into the installed capacity that we would assign to these locations, and then we get an output. And you can see actually from this, which is quite an interesting demonstration, even if we put two offshore wind farms opposite sides of the UK, they are producing roughly the same kinds of amounts of energy at the same times, which is really important. So we can do this for all number of locations that we want around the UK. This is actually based on an assessment of where the best potential for offshore resources in the UK are currently. And we can do the same thing for solar, onshore wind, to a degree other resources, although not completely, but they're not a large part of our scenario. It's really that wind that's very, very important, obviously. And we can do the same thing for our demands. So we've built up these profiles on an hourly basis over that 10-year period. And then we look at whether or not they match up, and they don't. In fact, they don't match up very significantly. We have huge surplus energy generation, but we also have absolutely massive shortfalls at various points. And quite rightly, everybody has been very concerned about this and don't like the answers that go, well, you know, we'll just buy electricity from someone else when we need it, and then we'll make massive profits by selling our excess electricity to someone else. I think we can all agree that that's not the solution to this problem. We can do some basic checks with our model. We can look at what happens on particular days at particular hours. So this is our best hour. This is where we produce the maximum amount of energy. It's the 22nd of May in 2011, which is a Sunday. So our demand is already very low on Sunday. We don't do very much in the UK on Sundays. You can also see from this photo, this is a tourist shot, actually, from the south coast. It's nice blue skies, very sunny. So we've got probably pretty much near a maximum of solar energy generation capacity. It's been very warm. Nobody's turning on their heating. Probably people are having cool showers instead of hot showers. And also it is incredibly windy. So very impressive wind speeds, which explains a lot. In contrast, we can also look at our worst hours. So this is the 21st of December 2010 at 8 AM, which I don't have a photo of, but probably looks a bit like this. Sun's not up yet. There's barely any generation from solar. It's also the coldest December for the last 100 years in the UK. There's a massive buildings heating demand, and there has been for a while. And yeah, okay, so they don't really write newspaper articles about whether or not it's a not very windy day. So I just made this up. But it's not very windy, okay? So our offshore and onshore wind farms are not producing very much energy, which is why we have a massive deficit. So basically, we can kind of plot all of these hours in our model, and we can ask how much of our hourly demand is covered by what we're supplying. 83% of the time, we have a surplus. It's a lot. In terms of amount of energy, it's a large amount of energy. In terms of the amount of time that we have a surplus, it's a large proportion of the time, and there are some reasons for this. One is that when I take you through the backup processes that we use, you will find out that they are very inefficient. We actually lose about 50% of the energy that we put in. We also have other demands that we're trying to cater for using some of this electricity. Because we're trying to decarbonise, but there are some areas that we can't use electricity for example, freight, aviation, some industrial demands, then we find that we actually can use some of this excess electricity quite cleverly to mean that we can, our demands for biomass are lowered. And also we have a question mark over things like shutdown time. If the winds are too high, then we probably need to shut down some of our resources. We haven't implicitly modelled that in the scenario, but we need to make sure that there's a bit of leeway there. But this is what really concerns us. This is the thing that really gets people concerned, is this shortfall, and it is a big shortfall. For 1% of the hours that we modelled, there's a shortfall of greater than 35 gigawatts. And it's that 17% of the time where we're not meeting demand that we're trying to cater for. So first of all, we find that there are some short-term fluctuations. So we're looking at sort of like hour-to-hour things that don't match up. And we find that helpful here, we've got demand-side management, smart charging of electric cars, for example. And we've also in the UK got some, but not a huge amount, of pumped hydro storage. We've also developed in our heat networks in the scenario some heat storage. And this It helps us out, but it doesn't solve the problem. So it helps us out in terms of we've got an additional 3% of the time covered. That's great. And we've capped our peaks, which is really helpful because actually when we get to the final solution of what's going on, the smaller the amount of energy that we require here, then the less stuff we have to install to cater for it. So it's helpful, but it won't solve the problem for us. And when we look to longer term fluctuations, so I'm talking needing to store energy for anything between weeks to months at a time. We need large amounts of storage capacity. We need a flexible and quickly dispatchable backup. The wind, particularly, and the solar energy goes up and down very, very quickly. We need a responsive system. We need something that can actually cater for that very, very dynamic change in supply and change in demand. Gas. Gas seems like the obvious choice. It allows storage of large quantities of energy, particularly in the UK. We have already a gas network. And gas turbines allow for flexible dispatch. We don't quite have the right kind of gas power stations in the UK currently, but there are in other areas of the world gas power stations that you can ramp up and ramp down to about 50% capacity in about an hour, half an hour. So you can react very, very quickly. The question about gas is obviously that it needs to be carbon neutral. We've made this rule. We need to be 100% renewable. And so we create our own gas. Instead of using natural gas out of the ground, we try and create carbon neutral synthetic gas. Hydrogen is an option, but actually it's not very easy to store that larger quantity of hydrogen. Methane is easier to store. As I've just said, we already have the infrastructure in the UK. So we employ the Sabatier reaction, which is basically taken carbon from biomass or from excess carbon dioxide from anaerobic digestion, for example, and kind of like upgrading it. So you're pushing the hydrogen in and you're converting this into methane and water, basically. And this means that two things, really. We need less biomass, which is really important for the UK because we don't have very much land. Secondly, it means that we actually use some of this surplus electricity that we've generated, which is really good. So I'm just going to home in on this particular area of this complicated flow diagram and take you through exactly how this system works. So we've got that biomass input. I'm just going to briefly show you our land use changes in the scenario, although I'm not going to go into them in detail. If we make changes to, for example, our diet, we can actually provide all of our food. Not quite all of our food. Be much more self-sufficient than we are now. We can reduce our imports from about 40% to about 15%. We can capture the remaining carbon in our scenario, and we can provide enough biomass to support our energy system in the UK. We take that biomass. We add the hydrogen from this electrolysis process using surplus electricity, and we create these carbon-neutral synthetic gases and synthetic liquid fuels, most of which, in our scenario, go to cater for these demands in industry and transport that can't be met with electricity. Only a very small proportion of them are actually burnt in backup power stations. This is actually, in total, about 3% of our electricity use over that 10-year period, and we use that backup about 15% of the time. And this is what our synthetic gas store looks like in the model. The amount of storage that we required is about 2 times the storage that we have today in the UK. And the backup turbine capacity is actually very similar to how many gas turbines we have in the UK at the moment. So it's not a small amount of infrastructure by any means whatsoever. And just a quick note here, you can see that really bad December when it was really, really cold. You can see how our gas store really goes down. We really, really needed that winter. So lessons in managing variability. What can we learn from this model? It is, of course, a first step. This is basically 8 to 12 months worth of research by 2 people who work part-time. So we know that we need to develop this more. We know there are still lots of questions that need to be answered, but from a first approximation, we can see that there are some solutions to this. We can also learn some really important things, so the things that we know don't really help us. Spreading resources out in different places doesn't help us. Using lots of different types of resources doesn't actually help us very much because they don't happen to, the sun doesn't suddenly come to the sky when the wind drops. They don't sort of balance each other out in that way, unfortunately. Demand-side management is really important, as are short-term storage, pumped hydro and heat, but they don't solve the problem. They help us with the real peaks in, the troughs when we have the real extremes of a shortfall of energy, but they don't actually cater for everything. And what we really need is this really substantial, flexible and quickly dispatchable storage. And I'm just going to put a note here is that baseload energy is not something that will help us in this scenario. So although I initially said from the beginning we have no nuclear in our scenario, this isn't actually something that would be good enough to be able to, we can't ramp it up and down in the same way as we can gas. And you just end up overproducing even more energy at times when you've got that surplus, 83% of the time. So from my perspective, that's not the best solution for this problem. We've still got more to learn. So we know that we can probably optimize this a bit. It's a bit weird optimizing to 10 years worth of weather data. So we haven't really played around with that very much. And if you have better suggestions on how we might do that, I'd really welcome to hear them. We also really wanted to do a sensitivity analysis because I kind of am accepting that in the future there will be some degree of climate change. I believe we're actually seeing the beginnings of it right now. And what we really need to do is simulate some of those extremes and go, hey, if we have 3 really bad winters in a row, how much storage capacity do we really need? And then we need to start asking things like, in those extreme shortage situations, what might we shut down? In the UK, we actually shut down some of our industrial capacity when we're short on energy already. Can we do that to a more significant degree? But we have shown to a first approximation, as I've said, that we can provide this reliable zero-carbon energy system. It is possible using our own resources. It is possible with 100% renewable technology. And actually, these things don't help us very much. But we do have to make some big changes. And just a final note, which is very brief. I understand the need for a roadmap. I'm not saying that this is the solution, but I do think it plays a part. And the thing that I think it plays a part in is basically related to what our aims are. We need to prove that some of these solutions do exist. Loads of people are A, misinformed, or B, don't know. And it's really important that we can tell people and explain the problems, but also potentially the solutions. It's also really important to support and inspire action that's needed desperately towards these kinds of solutions. And part of that, I really believe, is to help people see what living in these kind of circumstances would be like. What does it mean for my day-to-day life? What does it mean? Do I still get to go and see my family? Do I have to stay at home all day and freeze to death? So we kind of find, I guess, is that the future, unfortunately, for me anyway, doesn't look like this. It's not like sci-fi. It's not cool and exciting. But it's also not like this. We don't have to live in mud huts. You know, people are really afraid of this. This is what they see things like energy demand reduction as. But it's not the truth. We also have to say that we don't have to have a future that looks like this. We need some positivism, right? And when we do this kind of scenario analysis, it is a time shot, but we can say that the future probably looks a bit more like this, which actually, excitingly or disappointingly, depending on how you look at it, is probably more similar to that than we'd expect. Thank you.